Good morning, students. So today we are going to start with the next session on perturbation theory. So this is about degenerate energy levels. So in the last class we were discussing about non-degenerate energy levels, and for one wave function we will have one energy. So this is for non-degenerate energies. But here there will be many wave functions, but there will be only one energy. So what we call this as degenerate energies. So energies are degenerate. The energy is degenerate. In certain cases, we'll be using degenerate levels. Especially for the ground state, we'll be going only for the non-degenerate levels. And there are few examples we can say about degenerate levels. This is about the Zeeman effect and Stark effect. Spectral lines are split into its own components in the presence of magnetic field is known as Zeeman effect. The same idea in the presence of electric field is known as Stark effect. Okay. Now that application of magnetic field and application of the electric field are perturbation. The moment when you are going to apply the perturbation, the degeneracy will be removed, but not fully. Sometimes it will be partially also. In Zeeman effect, the degeneracy will be fully removed, whereas in the Stark effect it will be removed only partially, which we will see in the later classes. So as I said earlier, we have many wave functions. There will be a single energy. This energy is known as degenerate energies. Suppose you have ground state wave function. So linear combination of say these wave functions. So we have linear combination of these wave functions. Corresponding eigenvalues are given by this equation. You just look at the eigenvalue equation. This eigenstate is phi n1. Here the eigenstate is phi 1. Okay, phi n. Here eigenstate is phi n2. Here the eigenstate is also phi n2. Here eigenstate is phi n3. See, all the three states are there. We have different eigenstates. But what are the energies? Energies are the same. So they are called as degenerate levels. Suppose if you have two states, two bases. If you have two states, that means two bases. Then what we call this is two-fold degeneracy. So for example, just take there are two bases, two eigenstates are there, phi n1 and phi n2. Then we have the same energy. This will exist only for the two wave functions. Then what we call this is two-fold degeneracy. Similarly, we can go for three-fold, five-fold degeneracy, n-fold degeneracy. So something like that. So this is the idea about degenerate energy levels. So we have considered only one systems with non-degenerate in the previous section. Of course, we discussed about the non-degenerate case for the perturbation theory in the previous section. So now we are going to apply the perturbation theory to determine the energy spectrum and the states of the system. Okay, E and psi, whose unperturbed Hamiltonian is degenerate. So now we are going to have degenerate energy levels. The unperturbed wave function psi n0, okay, is a unique one in the non-degenerate case. When a degeneracy exists, so there will be a linear combination of degenerate wave functions which can be taken as a unperturbed wave function. So this will be your unperturbed wave function, and that will have degenerate. There will be two wave functions are there. Okay, two wave functions are there. So linear combination of degenerate wave functions. For simplicity, we are going to consider the case En0 is two-fold generation. So we are going to take only two wave functions for the simplicity. We can also go for three wave functions, four wave functions, and so on. But we are going to have only two wave functions for the simplicity. Okay. So let psi n0 and psi l0. So both are eigenwave functions corresponding to the eigenvalues En0 and En0. So this will be the energy for this wave function. This will be the energy for this wave function. For the degenerate case, there will be two wave functions. These two should be equal. Okay, for the degenerate case. Now, as I said, this is the linear combination of the wave functions we just now we discussed. Okay, where C n, Cl are some constants. Now we know about the first order correction from the non-degenerate case. So we have already discussed about this equation. This is the first order correction for the non-degeneracy section. We have already discussed. Okay, now we are going to replace psi n 0. We are going to replace psi n 0 with psi 0. So instead of psi n 0, we are going to substitute this expression. I repeat, instead of psi n 0, you just substitute psi 0. So we are going to substitute for this. Okay, this time let it be. This is psi 1. This is psi 0. Ground state wave function. This is first order. Okay, we are going to replace this alone with this linear combination of wave functions. Okay, is it okay? So this term, because this is psi n1 is here. Okay, we are going to keep as it is. Only psi n0 alone is replaced by this linear combination of these two wave functions. So now, as I said, this term is, let it be like this, h0 psi n1, let it be like this. We are going to take the ket on both sides. So now we are going to replace this by this. Okay, this by this. So h1 operator operates on psi n0, which is nothing but this. Okay, this term, first term, plus the first term I written as a second term, which is equal to en1 psi n0. So en1, instead of psi n0, you substitute this. So just you will get the first term, and this one let it be like this, en0 psi n1. Okay, equation 4.36. Now just operate this equation with bra psi n naught. Okay, operate this equation with bra psi n naught on both sides. So we will have psi n is a constant. I have pulled out Cn. Then psi n naught, bra psi n naught, h1 is here, operates on psi n0. So hn sandwiched between ket psi n naught and bra psi n naught. So expectation value. Okay, for the first order Hamiltonian. Okay, and this term. So this term I have written is exactly like this. So you just pull Cl out. So this will give you bra psi n naught h1 psi l0. Okay, this term. And the next term, let it be like this, the same term. Operate this operator. This operation is a bra psi n0, and we have h0 acts on psi n1. And this term. So this term en1 and the first term, that will give you Cn en1. En1 is a number value, so I have pulled out. So this operator operates on this one, will give you psi n0 get psi n0 and bra psi n0. And the next term I have written next term as exactly like this. Okay, you have as usual Cl, you pull it out. En1 is the value I have pulled out. So remaining thing will be your psi n0 psi l0, psi n0 psi l0. The last term I have written exactly like this. I have pulled en not out as it is a number pulled out. Now look at this one. This is psi n with psi n. Answer will be 1, because both the indices are the same. You have to use Kronecker delta function. Both n equals m, answer is 1. N is not equal to m, answer is 0. So you will get 0 here. There you will get 1. So we will have only 3 terms. This term, we will have 4 terms. 1, 2, 3 terms on left hand side, and right hand side we will have 1 term. Okay, is it okay? 4.37. So we have only 3 terms on right hand side, and this term also we have 1. This term. So Cn en1, Cn en1 multiplied by 1, that will give you same number. So left hand side we have 3 terms, right hand side we have 2 terms. Is it okay? Any doubt? Now we will go for third term. So since h0 is Hermitian, and eigenvalue equation for third term is given by this equation. Correct? h0 acts on psi n1 will give you en0 psi n. So this is we can write. So just replace this one. Replace, instead of this, just substitute here. You will get this term. This term let it be like this. The second term also on left hand side let it be like this. Third term we are going to replace with this one, and the remaining terms let it be like this. And this term and last term will get cancelled. Look over the terms. en0, bra psi n0, psi n1. They are also the same term. So both will get cancelled. So you have 1, 3, 1, 2, 3. Only 3 terms are left out. Is it okay? Now we are going to combine. Now combine these 2 terms. Now you will have This term can be written as HNN because H1 sandwiched between brass iron and Ketz iron. Okay, so this can be written as HNN matrix element HNN1. Okay, then we have CNEN1. So I can take this term this side, and I can take Cn as common. I can write this term. Is it okay? This term can be written as HNL. Okay, because sandwiched between psi L0 and psi N0. So this term matrix element can be written as HNL, and you have Cl. Is it okay? Have you understood this equation 4.40? So I combined this term and the last term, okay, and I have written this expression, and this term can be written as exactly like this. And this is a matrix element. HNL stands for sandwich between N and L. Okay, states N and L. HNN stands for the matrix element sandwiched between N and N states. So that's all. Similarly, and we have operated this operation, correct? Brass IN0, and we have obtained this equation. Similarly, you operate psi L0, brass IL0. Here we have operated brass IN naught. Here you are going to operate psi L0. You will get this equation. So that will be your assignment. The same procedure, follow the same procedure. You will get this equation. So these two equations we are going to solve for Cn and Cl and remaining energies. Is it okay? Any doubt? So we have two equations. Two set of simultaneous equations, and we are going to solve for the coefficient Cn and Cl. And we will get a non-trivial solution of these two simultaneous equations, and if the determinant equal to 0. So if the determinant of the coefficient will vanish, we will get a non-trivial solution. We have already studied in mathematical physics. So just take the determinant of both the equations exactly like this. So taking the determinant. So is it okay? We are going to take the determinant and diagonalize the equation. Diagonalize this matrix. This is a secular equation. Diagonalize this matrix. You will get energy eigenvalue exactly En plus or minus 1. We are going to simplify this one in the problem. So at the time you will come to know. Okay. So we have used minus b plus or minus root of b squared minus 4ac divided by 2a. Okay. Plus or minus. So plus stands for one energy, minus stands for another energy. We have separated the energies, one for plus, another one for minus. Okay. So En plus stands for En. For the another state El, which is equal to En minus. See, look at this expression. We have, this is a unperturbed energy En0 operates on psi N0, correct? And En plus, if you are going to add these two, that will give you En. Okay. Similarly, if you add En minus, you just add these two, that will give El. So we have separated the energy. See, each energy. See, this will have one energy and that will have another energy. This energy for En, that energy for El. We have separated the energy. For particular wave function, we will have one energy. So thus the perturbation removes the degeneracy. So earlier we said linear combination of N and L. We have used two wave functions. We have obtained only one energy. Correct? We have used two wave functions. One is psi N, another one is psi L. Okay, that is Cn, Cl. We have used. But now we have obtained En, which is this expression, and El we have used another expression. So we have separated. That means for each wave function there will be a separate energy. So the perturbation removes the degeneracy. So perturbation will always remove the degeneracy. Either it can be fully or it can be partially. For Zeeman effect it will be fully, it will remove. Whereas in Stark effect it will remove only partial. Still there will be degenerate levels, even though perturbation is there. Okay, so this is the idea. Is it okay? So now little bit digression. Both the energies will be real as a diagonal matrix elements of Hn and HLL of the Hermitian operator are real. Of course we know. Suppose if you use this condition, Hn equals HLL and HNL equal to 0 in this expression. If Hn equals HLL, and the next one will be HNL equal to 0. So this term will not be there, correct? If you use this one, this is equivalent to this, and if you make this equal to 0, you will not get this difference. So it will become 0. So this term will be equal to this, correct? So you will have 2 times of En plus or minus, which is equal to 2 times of HNN, correct? Or HLL. See, look at this condition. We have HNL equal to 0. Then another condition is HNN equals HLL. So if HNN equals HLL, we have 2 HNN, correct? If 2 HNN, these 2 and these 2 will get cancelled. We will have HNN equals EN. HLL equals again EN. Is it okay? Come on. This argument is like this. If both the terms are equal and this term is equal to 0, we will have this term. We will not have this term. This will become 0. Only this term alone will exist. If HNN equals HLL, it becomes 2HNN. That 2 will get cancelled. You have HNN equals EN. Suppose if we go for HLL, then HLL will become again EL, correct? EL. So it says that the degeneracy is not removed in the first order. Still, if this condition is satisfied, okay, that's all. If it is not satisfied, of course we have removed already. Okay. Now when the two roots of equation 4.43, so we'll have 2 by 2 matrix. So we'll have 2 roots, correct? So if the 2 roots of equation 4.43 are distinct, say they are different, that can be used to calculate the ratio Cn by Cl. So we can go with Cn by Cl, and the normalization constant C1 square plus Cl square equals 1. So these two will give us, using these two conditions will give us the values of Cn and Cl. We can get the values. If we use these two conditions, we will get the coefficients Cn and Cl. So it can be determined. And associated wave energy will be En naught plus En plus and En naught plus En minus. So we have separate. Okay. In a similar way, the combination associated with the level, that also can be evaluated. Okay. Suppose for N system, for F system. So we have so far we have studied only for two-fold degeneracy. Okay, two-fold. And this is for N level system, for say F homogeneous linear equations. Okay, F fold. So we will have the determinant should be equal to 0. Okay, and this is for F levels, for N levels, F levels. Okay, so this is for 2 levels. Okay, two-fold degeneracy. This is for N level or F level, doesn't matter. So we can apply for 2 by 2 matrix or 3 by 2-fold degeneracy, or 3 by 3 matrix for 3-fold degeneracy. For F level we have F by F d-fold degeneracy. Okay, is it okay? So let us calculate the 2-fold degeneracy in detail. Okay, so this we have already seen earlier. So this equation. Okay, so I have taken exactly like this with the separation of, there it is Cn Cl. But here we have written as C1, C2. Both are the same. So different coefficients. So this matrix we have taken from equation 4.43. Okay. We just solve this equation. So we will have H11 minus E1, C1, correct? Plus H12, C2. So this is one equation. And if we multiply matrix operation, that will give you this another equation. And we will get a non-trivial solution if we take the determinant equal to 0. So this is what we studied earlier. Okay, this is what we studied earlier. So just to take the determinant, multiply these two minus multiply these two. So we are going to multiply these two with a minus sign of, we are going to multiply these two. So here it is 2 terms, multiplied by 2 terms will give you 4 terms, correct? H11 multiplied by H22, then H11 multiplied by E1 minus E1 multiplied by H22, then last term will be plus E1 square. The last term let it be like this. Okay, now E1 square, this E1 square is here. Okay, now in the H11 E1, H22 E1, you pull E1 out, so this will give this. This term is a constant and this term also will be constant, you pulled out. So this is quadratic equation. Okay, quadratic equation. So where E1 square, E1 is here, constant is here. We can use minus d plus or minus root of d squared minus 4ac divided by 2a. That formula you can use to get the value for E1. See here E1 is there. Okay, we can get the value for E1. So we have used minus B. See, minus B. So minus minus plus, that will be plus. So minus B plus or minus root of B squared minus 4AC by 2A, that formula. Just divide 2 separately, that will give you this equation. Okay. Now plus or minus is there. So plus stands for En1, minus stands for E21. So we have separated these two energies. We have separated. So this is one energy, this is another energy. And another energy level, we can say. Now the total energy will be En0, which is the ground state, plus En1. Okay, this energy. Or otherwise, E equals ground state energy plus E21. This is another energy. Is it okay? So this is for the two-fold degeneracy. Very simple one. So in the diagram, this is your ground state energy. Ground state energy En0, which is a linear combination of these two wave functions. C1 phi n1 plus C2 phi n2. Linear combination of these two wave functions. So we have two wave functions, phi n1 and phi n2. Linear combination of these two wave functions. Now we are going to apply perturbation. So this is the application of perturbation. When you apply, the moment when you are going to apply the perturbation, we have obtained two energy levels, correct? Two energy levels. So one energy level goes like this, then another energy level goes like this. So we have separated these two energy levels. Okay, here same energy, two wave functions. We have separated the energy now. What about your wave function? Your wave function will be, this is your wave function for the upper level, and this is your wave function for the down level, okay, below level. And this can be considered as phi plus, and this can be considered as phi minus. See, look at here, phi plus stands for one energy, phi minus stands for another energy. We have separated the energy. I repeat, we have single energy, we have two wave functions. After the perturbation, we have separated the energies, and this wave function stands for this energy, and this wave function stands for this energy. So for each wave function, we will have each energy. So degeneracy is removed. Here there is a degeneracy. Two wave functions, we have a single energy. Degeneracy exists. After the perturbation, we have removed everything. See, we have already done the calculations which you have seen earlier. And single wave function, single energy, single wave function, we have single energy which are separated. So thus we can remove the degeneracy. Is it okay? So thus the perturbation removes the degeneracy. Is it clear? So 4.46, the determinant, okay, is the fth degree equation in En1. En1 stands for the first order energy corrections, energy levels, energy corrections. And in general, it has a fth different real roots. So we will have different roots will be there. For two-fold degeneracy, we will have two roots. For f, we will have f roots will be there. For n level, we have n roots will be there. These roots are the first order correction to the energy eigenvalues of En plus. To find the coefficient Cn, we will have to need to substitute these roots into equation 4.46, that determinant value, and then solve the resulting expressions. So this is what we have done. Knowing these coefficients, we can then determine the eigenfunction psi 0 of H in the zeroth approximation. Okay. So in this way, the perturbation lifts the degeneracy. The perturbation lifts the degeneracy. The lifting of the degeneracy may be either total or partial. Okay, it can be total or partial depending on whether all the roots of equation 4.46 of only some of them are different. Okay, so this is the conclusion. So degeneracy can be either removed totally or partially depending on the situation. As we discussed earlier, for a Zeeman effect, it will be totally, it will be removed. Whereas in Stark effect, which we are going to study in the next class, it will be removed only partially. Is it okay? So now we'll solve for only one problem. We have this problem. Given the matrices for H0, so this is for the ground state, unperturbed term. Unperturbed Hamiltonian is given by 2 by 2 matrix, E0, 0, 0, E0. And you are going to apply the perturbation. So perturbation is H1 equals 0 minus A minus A 0. Okay. And the orthonormal basis 1 and 2. So these wave functions should be always orthonormal. Okay, as I said, linear combination, it means they are orthogonal to each other, orthonormal. Suppose if we consider two bases, ket1 and ket2. and we are going to determine the energy eigenvalues and the energy eigenfunctions. We are going to determine. So your total Hamiltonian will be adding these two, unperturbed plus perturbed Hamiltonian. So this is unperturbed, this is perturbed. You add these two, that will give you total Hamiltonian. Is it okay? Now, as usual, we will have to take the determinant. When you are going to take the determinant, we will have to use this h minus lambda I, which is equal to 0. So this matrix will become E naught minus lambda minus A E naught minus lambda, which is equal to 0. So now you are going to take the determinant. So E naught minus lambda square, correct, minus plus, that will give again one minus is there, so minus A square equal to 0. So this equation can be solved, quadratic equation can be solved. So expand this one, you will get this. See, expand this one. A minus B whole square formula, expand this one. So after that, just we can write this equation as lambda square minus 2 E naught lambda plus E naught square minus A square. So this will be our constant. We can get the value for lambda. Again use minus b plus or minus root of b square minus 4EAC by 2A. So we will get this. So plus is one energy and minus is one energy. Okay. So now what we can do is just to pull 4 out. So that will be 2. These 2. So divide by 2, that will give you E naught, that will get cancelled. You have E naught plus root of E naught square minus E naught square minus A square. Just take this minus n inside. So minus E naught square plus A square. This one and this one cancel. So you will get E naught, this E naught plus A. Root of A square will give you A. So E naught plus or minus A. So one answer will be E naught plus A. The another answer will be E naught minus A. So we have two equations. Matrix is 2 by 2 matrix. Surely there will be two roots. So we have two roots. Okay, one is E naught plus A, another one is E naught minus A. See, it lifts. Okay, it lifts. One is plus, another one is minus. When I am going to apply the perturbation, the degeneracy, see, it's lift. So it is lifted. E naught plus A, another one is E naught minus A. So these are your eigenvalues. Okay, so eigenvalues, the first one is determine the energy eigenvalues and the energy eigenfunctions. So we calculated the eigenvalues. Now we will go for the eigenfunctions. So let 1 and 2, correct? Ket 1 and ket 2. So let psi 1, that can be written as ket 1. Okay, let psi 1 equals xy. We'll just keep it as it is. Be the eigenfunction with the values lambda E naught plus A. We are going to consider. Now use eigenvalue equation. So eigenvalue equation is given by h psi equals E psi. So your h psi equals E psi. Okay, eigenvalue equation. So here there's a mistake. It must be E naught plus A. It's correct. No, it's correct. Lambda, instead of lambda we have written E naught plus A. Come on. Lambda E naught plus A. Here it must be lambda xy. Instead of lambda we have written the first one because we have taken ket psi 1 as xy. See, ket psi 1 as xy. So that's why we have written as lambda. Instead of lambda we have written E naught plus A. Is it okay? So E naught plus A xy. Now you just take the first equation. So that will be E naught x. E naught x. So that will give you minus ay, which is equal to E naught x plus ax. Ax. First equation alone. If you take the second equation also, you will get the same. Okay. If you get the second equation also, you will get the same. So we are going to take the first equation. This equation alone. So we will get E naught x. This E naught x will get cancelled. This a and a will get cancelled. You have x equals minus. And we have kept already psi 1 equals xy. So psi 1 equal to xy. So instead of y, you can substitute minus x. So this will be our eigenvectors and normalized eigenvectors. There are two components. You will have to go with 1 by root of 1 square plus 1 square. So 1 by root 2. So here 1 by root 2. And this is your eigenvector. Okay, we will have to change into eigenvector. That will give you 1 minus. Okay, so eigenvector for the first wave function. Psi 1 equals 1 by root 2, 1 minus 1. Okay, so we have computed for psi 1, that is ket 1. Okay, using this eigenvalue. Similarly, we can go for another one, ket 2. Okay, that will give you E naught minus A, that is E naught plus A. Now it is E naught minus A. Okay, so this is for get 2. Okay, we are going to get. So as usual, simplify this matrix equation, that will give you this, and this one will cancel, minus minus will get cancel, a also will get cancel, you will have x equals y. So let psi1 equals xy xx. So eigenvector you have to find out, that will give you 1 by root 2 1 1. Here it is 1 minus 1, here it is 1 plus 1. So we have found out now eigenfunctions for separated eigenenergies. So this is your eigenfunction and this will be your eigenvalue. So this is your eigenfunction, this will be your eigenvalue. See here, this is 1 minus 1, 1 minus 1, linear combination of these two. So linear combination of these two. This is psi 1, psi 2. This is ket 1, ket 2. So ket 1, ket 2. Okay. So your psi naught ground state function, which has a combination of psi 1 and psi 2, after the perturbation, separately we have written separately as E naught plus A the energies, and wave function is exactly like this. And for these energy levels we have the wave function like this. So for this wave function it represents the eigenvalue. For this wave function we have the energy eigenvalue. Separately we have written. So we have removed the degeneracy. Here it's a linear combination of ket 1, ket 2 are the linear combination of ground state wave function. So for this wave function also we have energy. For this wave function also we have the energy. But here after the degeneracy, what happens? Here separately we have written. For this wave function we have energy. For this wave function we have different energy, E naught minus A. It lifts the degeneracy, and degeneracy is completely removed. So this is non-degenerate levels, exactly like this. So this is degeneracy, that is non-degeneracy. Very important thing is, and these two wave functions should be always orthogonal to each other. So that's the conclusion. Okay, so we'll stop today and we'll continue our session with the Stark effect in the next class. Bye students.